In this video, we are going to implement a lattice-boltzmann solver for the Kármán Vortex street behind a cylinder in Python using the JAX deep learning framework in order to make that run really fast. And we will do so in roughly 300 lines of code. So let's get started. Hi and welcome to this new video. The lattice-boltzmann method is a fairly recent approach to computational fluid dynamics. It differs from classical ones like finite differences, finite volumes, or finite elements in that it looks at a mesoscopic scale of fluid motion. That means it is somewhere in between the macroscopic scale, where those classical discretizations are based upon, and a microscopic scale, which is based on statistical mechanics. Here we want to use the LBM method to simulate the Kármán vortex street that is happening behind a cylinder, here in this case in 2 dimensions. And it works like this, that we have a rectangular domain with an inflow on the left end. So we have horizontal velocities entering our domain there. Then we have an outflow on the right, such that our fluid can exit the domain, and we link our top and bottom boundary using periodicity. And then there is an obstacle centered in our flow. You can think of it as a slice of a 3-dimensional cylinder. And our flow has to surpass this object. And then because of the boundary layers happening around the cylinder, we have vortex shedding in the wake of the cylinder, which we can beautifully visualize. And the lattice-boltzmann method works like this. We discretize our 2-dimensional domain into a mesh, or in our case, we will use a Cartesian grid. For each vertex, we are going to associate 9 discrete velocities, which are based on the mesoscopic interpretation of fluid motion. And then the task of our simulation is to evolve these 9 discrete velocities at each point in the mesh over time. And we will do this in the following steps. First, we apply the outflow boundary conditions on the right boundary. Then, out of the mesoscopic quantities, we can compute the macroscopic quantities, density and velocity. And remind yourself, the velocity here is a 2-dimensional quantity because we have an x and a y component. Then we can apply the inflow profile, which is a Dirichlet boundary condition. So we prescribe the fluid flow on the left boundary. And for this, we will use the Suchet boundary condition scheme, which is commonly used there. Then, by the help of the macroscopic quantities, we can compute the equilibria velocities, or more precisely, the discrete equilibria velocities. These equilibria velocities then enter the so-called collision step, which is according to Bartnagar, Gross and Krog, and it's also called the BGK operator. That might sound a little strange now, but I think it will get clear when we implement that. After this, we do so-called bounce-back boundary conditions on the cylinder obstacle, so on the boundary of this obstacle, because there is a no-slip boundary condition attached to it. So the fluid cannot enter the cylinder, and of course it has the same velocity as the cylinder on the boundary, which is 0. So it is at rest on the boundary of the cylinder. The next step, the 7th step, is to stream alongside the lattice velocities in order to move our mesoscopic velocities through the domain. And then we will just repeat this for as long as we want to simulate. The step of the collision and the streaming are the 2 crucial steps in every lattice-boltzmann method. I already mentioned the discretization of our mesh and the association of the mesoscopic velocities at each vertex, and there are particular schemes within lattice-boltzmann methods. We will use a so-called D2Q9 grid, which is the 9 discrete velocities that I mentioned earlier. And you can think of them somehow geometrically, that each of the numbers you see here is associated with the direction the mesoscopic velocity is flowing. So, for instance, number 1 is pointing to the right, which would be a positive x direction. 2 is upwards, which is a positive y direction. 3 is to the left, negative x, and so on and so forth. 5, for instance, then would be positive x and positive y, and the 0 velocity does not have any direction, so it is just non-directional in the center there, and it is needed in order to make this D2Q9 grid compatible with the macroscopic definition, the Navier-Stokes equations. Accordingly, we have to use the following arrays throughout our computation. For the macroscopic velocity, we will have an array that is of shape number of points in x, number of points in y, and then 2, because we are two-dimensional. And then for the discrete mesoscopic velocities, we have 9 discrete velocities associated with each vertex. And then for the density, which is just a scalar, we just have a value for each vertex in the domain. Throughout the implementation, we have a couple of computations happening. So we can compute the densities out of the discrete velocities by summing over the discrete velocities. So we say the density at each node is the summation over this very last axis. And I think this makes sense. Then we collapse our 9 discrete velocities into one scalar quantity. We can compute the macroscopic velocities by summing over the discrete velocities multiplied with the so-called lattice velocities. We will see about that in a second, and divide by the density. And then we have a function for the equilibrium in order to get our equilibria discrete velocities. This is a consequence of a derivation that is rather lengthy, so we will just accept the results here and implement it. If you want more detail, I will also leave some nice literature in the video description. The BGK operator is given here. And here I just have a summary of all the quantities that are involved. And lastly, we want to define our flow by the Reynolds number. The Reynolds number is a dimensionless quantity which can be used in order to characterize the flow. And it is given as a characteristic velocity times a characteristic length scale divided by the kinematic viscosity. And since we want to prescribe the Reynolds number, we can infer our kinematic viscosity based on that. And then we compute the relaxation factor, which is this omega that appeared in the BGK operator, according to this formula, which is also a result of a rather lengthy derivation. With this said, let's finally start implementing. So first, let's do all the imports that we need. I already mentioned we want to implement this in JAX. So we need JAX as well as JAX.numpy as JNP. If you don't know JAX, that's not a problem because we will use it mostly in its NumPy interface, so it is quite similar to NumPy if you are familiar with that. It just has 1 or 2 things where it might be a little bit different, but I think they will get clear based on the context. And the reason we are using JAX is that it's by orders of magnitude faster than by implementing this in NumPy. Then we will use matplotlib.pyplot as PLT in order to visualize our results. Then I will use cmeasure as CMR. I like their color maps, but you don't have to use that. And I will also use TQDM, so from TQDM import TQDM as a super simple progress meter. Then let's define some constants of our simulation. So we want to do 15,000 iterations, so 15,000 iterations. We want to start with a Reynolds number of 80. Our grid is based on 300 points in x direction, so n points x are 300, and n points y shall be 50. So we have a domain that is 6 times longer than it is tall. Then we have to place our cylinder somewhere in there. So we say cylinder center index x, and we want to put that on a fifth of the length of the domain. So we say n points x divided by 5. And here I'm using an integer division, so double /. Then we have to define the cylinder center index in y. And here I want to just center it in the y direction. So we do n points y integer divide by 2. And then we have to define its radius by saying cylinder radius indices. And here I will just say n points in y integer divide by 9. So this will be the radius. And I say indices here because here we are not working in physical spaces like saying in meters or something, but rather say we do 1/9 of the number of discretizations in y direction. Then let's define the horizontal inflow velocity. So max horizontal inflow velocity. And this will be 0.04. And then just some flags. We want to visualize it. So let's say visualize equals true. And then we say plot every n steps being 100. So only every 100 iterations. And then we want to skip first n iterations. And I will put this to 0. And I will show later why we need that option. Now let's look at the grid. I just copied this from before. So remind yourself, these are the discrete mesoscopic velocities associated with each vertex in the grid. And now we have to define something based on that. First, let's start by saying we have 9 discrete velocities. So n discrete velocities is 9. Then we have to define the lattice velocities. And for this, we will use an JAX numpy array. So in other words, a numpy array, but in the JAX implementation. And here we have to define in which direction each of the indices are pointing. And remember, we have an x and y component of our grid, and we said that the 1 velocity is just pointing to the right. So it has an 1 component in the x direction and the 0 component in the y direction. So let's do this like this. We say it is 1 in x direction and it is 0 in y direction. So I want to create a 2-dimensional array, in other words a matrix, which is of size 2 by 9, which associates each of the discrete velocities with their macroscopic directions. And of course here you see I kind of made a mistake because we have to start with the 0 velocity, which is in the center, and this one has 0, 0, because it's neither pointing in x nor in y. Then let's go on to 1. We already said this was 1 and 0. Then how about 2? So let me also use double spaces here. So how about 2 then? So 2 has 0 in x and has 1 in y. Let's go on to 3. 3 is pointing to the left, meaning that it has -1 in x and has 0 in y direction. And then the 4 has 0 in x and has a -1 in y direction. Then let's go on to 5, pointing to the top right, which will be 1 in x and 1 in y. And then 6, top left, which will be -1 in x and 1 in y. And I think you get the pattern. 7 will then be -1, -1. And lastly, 8, which is our 9th velocity, will then be 1. And here we will have a -1. Now we have to define which of the velocities are the opposite velocities to 1. So for instance, velocity index 3 is the opposite to velocity index 1. 7 would be the opposite of 5. So let's first start by defining the lattice indices. And here I will use another array and just say, okay, these are straightforward my indices. So I would just say 0, 1, 2, 3, 4, 5, 6, 7, 8. And this is just a 1-dimensional array, aka a vector. And then I can use that as a help to define my opposite lattice indices. And these are then equal J and P array. And then the opposite of 0 is 0 because it does not have an opposite one. But for 1, it is 3. For 2, it is 4. For 3, it is 1. And for 4, it is 2. And then for 5, it is 7. For 6, it is 8. And for 7, it is 5. And for 8, it is 6. And here we have our matching 0 to 0, 1 to 3, 4 to 2 to 4, and so on and so forth. And then we have to define these lattice weights. They will appear within the equilibrium computation. And these are rather difficult to derive. So I will just note them down. So we have a lattice weights. And they are given according to the following. So we associate a weight with each of the velocities. And for the center velocity, it's 4 divided by 9. And for the velocities 1, 2, 3, and 4, so the axis-aligned velocities, it will be 1 over 9. So I'll just note that down. And let me also put some spaces here. And for the other ones, it will be 1 over 36. So 1 divided by 36, 1 divided by 36, 1 divided by 36, 1 divided by 36, and so on. And they are a little bit out of the blue here. They are a consequence of the consistency of the lattice-boltzmann method with the Navier-Stokes equations, but we won't cover them in more detail, why they are the way they are here. So let me just add some more information. So these are the center velocity or the zero velocity, which has the zero index. And here we have the z-axis aligned velocities, which are 1, 2, 3, and 4. And here we will have the 45-degree velocities, which are 5, 6, 7, and 8. And then one last thing, then we're done with our constants here, which are the definition of velocities that are horizontal, that are vertical or purely vertical. So let's start by defining the right velocities, which are the velocities that are pointing to the right. And these are the velocities 1, 5, and 8. And you can take a look at that. So this is 1, 5, and 8. Then we have our up velocities, which are the velocities 2, 5, and 6. Let's also double check that. So 2, 5, and 6. Then we have our left velocities, which are another array. And this one is 3, 6, and 7. And then we have our down velocities, which are the following indices 4, 7, and 8. Let's also check that. 4, 7, 8. And then we also need the velocities that are purely vertical or purely horizontal. So I will call these pure vertical velocities. And these ones are 0, 2, and 4. And these are basically this vertical slice in the center. And then we have the same for the pure horizontal velocities, which are the following indices 0, 1, and 3. Okay, these are quite some constants that are involved in the simulation. Now let's start with the actual computations. So for this, I want to create 3 helper functions that we will use throughout the implementation. First one to compute the density, then one to compute the macroscopic velocities, and then another one to compute the equilibria discrete velocities. And the first function will be to get our density. So let's define a function that's called getDensity. And this function takes the discrete velocities and then returns the density. Let's look at the computation. So we said that we get the density by summing over the discrete velocities, so over all the 9 velocities, and they are in the very last axis of our array. So let's say the density is jnp.sum or numpy summation over the discrete velocities and then the very last axis. And then we can return the density. Let's do something similar for the macroscopic velocities. So we say define get macroscopic velocities. And this one takes the discrete velocities as well as the density. And then we can define the macroscopic velocities. So let's look at the computation that is happening. And if we look at that one here, we see the velocities are defined by 1 over the density. And then we have a summation of the discrete velocities with the lattice velocities. And remind yourself, the lattice velocities, that was this matrix that is associating the discrete with the macroscopic velocities. And so in other words, we have to do some sort of a matrix vector product here. However, we want to do this matrix vector product in a high dimensional space. Or in other words, we just want to batch it over the nx and ny axes that we have here. And for this, we will use the einsum, so a function in NumPy or JAX NumPy that is using the Einstein summation convention. It's called einsum. And this one first takes an operation string and then the 2 operands, which are the discrete velocities as well as the lattice velocities. And then in the operation string, we put in the axes of the discrete velocities, which are n and m, which let's say are the number of points in x and number of points in y, as well as q, which are the number of discrete velocities, which are 9. And then for the lattice velocities, we have a shape of d and q. So we say comma dq. And then we want to perform the addition or this matrix vector product over the Q axis, so that our resulting array has the shape NMD, with D being the macroscopic axis. So let's go over this once again. And I see here this shouldn't be a lowercase m. So the discrete velocities have the shape n points in x times n points in y times 9 discrete velocities. The lattice velocities have the shape 2 macroscopic velocities and 9 mesoscopic velocities. And we want to perform a matrix vector product over the discrete velocities, so you don't see them in the resulting shape anymore, such that the macroscopic velocities object is of shape NMD, which is number of points in x, number of points in y, and then the macroscopic dimension. And lastly, we have to divide by the density. So we say divide by density, and this will not work because the density is just a 2-dimensional tensor and not 3-dimensional. So we have to create a proxy axis in the very end. So we say JNP new axis and insert this ellipsis operator here. And now it will probably broadcast over this very last axis. And then we can return the macroscopic velocities. The last helper function we need are the equilibria discrete velocities. So we say get equilibrium discrete velocities. And this one takes the macroscopic velocities as well as the density. And then let's look at the formula, what is involved. So we say that the discrete velocity in the ith direction is given as the density times the lattice weight. And then this one in the bracket, which is 1 plus 3 times the projection of the macroscopic velocities onto the lattice velocities, plus 9 over 2 times this projection squared, minus 3 over 2 the macroscopic velocity magnitude. So let's compute c times u and the magnitude a priori, and then we can just evaluate the entire expression. Okay, let's do that. First one are, I will call them the projected discrete velocities, and we will use another einsam command for this. And let's leave out the operator string at first. And the involved two components are the lattice velocities as well as the macroscopic velocities. The lattice velocities are of shape dq, and the macroscopic velocities are nmd. That's what we computed here. And then the result of this computation shall be nmq, with q being the number of discrete velocities. Then we can compute the macroscopic velocity magnitude. And for this we will use jnp.linalg.norm by taking the 2 norm of the macroscopic velocities over the last axis, which is this q, or sorry, it's the d axis here that we have in our macroscopic velocities. And we want to take the Euclidean norm, so we say order 2. So with these two auxiliary quantities, we can compute the equilibrium discrete velocities. So we say equilibrium discrete velocities, and they are given according to the density, which we again have to add a batch axis in the very end in order to do the proper broadcasting. So we say ellipsis operator and then jnp.new axis, and then multiply that with the lattice weights, where we have to batch them over our points in x and points in y. So we say jnp.new axis, jnp.new axis, and then we do the colon in order to access all the lattice weights. Because if you take a look at the lattice weights again, although we use multiple lines for it here, it is actually just a one-dimensional vector that we have to batch over all our grid points in 2 dimensions. Then let's finish off the computation. We have to multiply that, and then we have the term in the brackets, which is 1 plus 3 times the projected discrete velocities, plus 9 over 2 multiplied with the projected discrete velocities squared, and then minus 3 over 2 multiplied with the macroscopic velocity magnitude, And here we have again to batch that over all the discrete velocities because it is just a scalar-based quantity. So we do ellipsis operator and then jnp.new axis. And we have to square that because if you look at the formula here, you see that it's also squared in there. And that one then concludes our equilibrium computation. So we can return the equilibrium discrete velocities here. With all this done, we can then finally start our main routine, which will be the actual simulation. So let's say define main, and then let's leave that empty for a second and implement the main switch. So say if name equals main, then execute the main function. And then what we have to do in the main function first is to enable double precision computation, which is disabled in JAX by default because it's not so common in deep learning. This can be done by saying jax.config.update and say JAX enable x64 being true. Okay, then let's look at the last entry in the documentation here, where we say we want to prescribe our flow with a Reynolds number. And we can use this Reynolds number and the other configuration in order to infer the kinematic viscosity as being the inflow velocity times the radius divided by the Reynolds number. And then we can compute our relaxation omega. So let's do that at first. So define the kinematic viscosity. So kinematic viscosity being, and this one is the following computation, we have the max horizontal inflow velocity multiplied with the cylinder radius indices, and then let's divide that by the Reynolds number. And then we can compute the relaxation omega, so let's say relaxation omega, and this one is 1.0 or 1 divided by 3 times the kinematic viscosity plus 0.5. And as said, this relaxation omega will appear in the BGK collision later on. So then let's define the mesh. So let's say define a mesh, and our mesh in x direction will be jnp.arrange of endpoints in x, and in y it will be jnp.arrange endpoints in y direction. And you see here we are not associating any physical quantities like meters with that one here. Then let's define our two-dimensional meshes using jnp.meshGrid, which is identical to what you would do with NumPy by entering the x and y mesh. And then we will just use the indexing ij here, which makes the differential operators that we will use later on more logical. Okay, now we need an obstacle mask. So this will be an obstacle mask, because if you look at the description of our problem again, that we have our cylinder in the center here. And later on, when we then evolve our discrete velocities, we have to somehow know where the obstacle is in order to apply these so-called bounce-back boundary conditions. So let's create a mask of an Boolean array basically, which has the same size as our mesh, but is true when this vertex belongs to the cylinder, and it is false if it is just a regular vertex. So let's say the following. This will be an array of the shape like x or y, but contains true if the point belongs to the obstacle and false if not. And we can use the vectorization semantics in NumPy or JAX NumPy to create the obstacle mask. And this will be comparing the distances or the positions. So we say jnp.square root of the x positions of each vertex minus the cylinder index in x squared plus, and then we have the y position minus the cylinder center in y also squared, and then we check whether the square root of this distance is smaller than the cylinder radius. And then we know this within the obstacle, and then it is true because this would evaluate to true, and if it was outside, then it would evaluate to false. And the last point in the preparation will be to define the velocity profile that we will prescribe at the left boundary, but just for convenience, we will create a profile at each vertex here by saying jnp.zeros of the shape n points in x, n points in y, and then 2. And then we set the y component of each velocity vertex to our inflow velocity. So we say velocity profile at, well, all x positions, all y positions, and then the 0 component, which will be the horizontal component, is the max horizontal inflow velocity. And that's at least how you would do it in NumPy, if you're familiar with that. But here we are using JAX NumPy, and in JAX you can't mutate arrays, so you have to create new arrays. And there is some approach in order to have some convenient shortcut there by saying that the velocity profile is the velocity profile at all points in x, all points in y, and then the 0 component dot set. And then it's basically doing the same as if you were doing the mutation that you know from NumPy. That was a long preparation. Now let's go back to the actual algorithm with its 7 or 8 steps. And we want to implement this algorithm as a function that I will call update. So let's define this function and say define update. And this function takes the discrete velocities from the previous iteration and updates them to the next iteration or the next point in time, basically. Okay, and the first step was to prescribe the outflow boundary condition on the right boundary. The outflow boundary condition is basically a Neumann boundary condition such that the normal derivative outwards facing on the boundary is 0, and the easiest way to do that is by just replicating the values on the boundary to the layer 1 node inwards to the domain. Okay, sounds a little bit strange. Let's just write that down by augmenting our previous velocities and saying these are the previous velocities at the boundary. So this is -1. So we are in x direction in the very last end. So if we look at this, this will be on the very end, so the last layer of vertices. And then we say all vertices in y direction. And we only want to do that for the left velocities. And then we say this shall be equal to the discrete velocities 1 layer before the boundary, all in y direction, and the left velocities again. So if you look at this one and you imagine there is this very last layer, and in these last layers we have 50 vertices, and with each vertex we have our 9 discrete velocities. We are setting the left velocities there to be the left velocities in this position, because then the flow cannot flow outwards anymore in the streaming step. Okay, second one was to compute the macroscopic velocities. So we say second macroscopic velocities. So we define the density in the previous iteration, or based on the previous values, as our getDensity function applied to the discrete velocities previous, and then we can get our macroscopic velocities in the previous iteration according to our get macroscopic velocities, and then use our discrete velocities previous and the density that we just computed. And of course, this should be the density previous. Okay, next step is to prescribe the inflow Dirichlet boundary condition using the Suchet scheme. So we say third point is prescribe inflow BC, or let's say inflow Dirichlet BC using the Suchet scheme. So this is done in the following steps. So this will be a little bit more complicated. I will leave out the discussion why we do it that way for another video. So just bear with me with that. So we say the macroscopic velocities in the previous iteration are the macroscopic iterations are the macroscopic velocities previous iterations at, and now we are at the very left, so 0. And here we say at almost all nodes in y direction. Here we will exclude the very top and the very bottom vertex in y direction, but for all discrete velocities. And here we want to set them to the velocity profile. So I think this makes sense. We say that the macroscopic velocity, which was this two-dimensional quantity, we say this one at the very left is given according to this velocity profile that we want to prescribe. But now we have to ensure that certain properties hold, which are defined by this Suchet scheme, and these augment the density there as well by saying augment the density. And we say that is the following computation. We compute the densities at the very left, but just for the purely vertical velocities by saying get densities on the discrete velocities previous iteration left end, and then all positions in y, and then only the pure vertical velocities plus 2 times get density on the discrete velocities previous very left in x and all in y, and then the left velocities, and then divide this by 1 minus the macroscopic velocities in x direction at the very left. So again, 0 means we are at the very left. So let me go here. We are here. And then the colon means we look at the entire boundary. And then the 0 in the end means that we're just looking at the x component of the velocity. So let's go down. And unfortunately, this does not work. We have to put in a transpose here. And that is because of the auto broadcasting that would otherwise be happening. But either way, just bear with me that this is the correct implementation for the Suchet scheme. And now we can use the macroscopic velocities that we just augmented together with density to compute the equilibrium discrete velocities. So this is step number 4, compute discrete equilibria velocities. So we say equilibrium discrete velocities, and this is get equilibrium velocities on the macroscopic velocities previous as well as the densities from the previous iteration, or that we just augmented here a bit. And now we have another step of the Suchet scheme, which is applied after the equilibrium velocities have been found. So I will just use another 3 here and say that this one belongs to the Suchet scheme by saying that the discrete velocities in the previous iteration are the discrete velocities in the previous iteration at, and again at the very left, so 0 and then colon. And now we want to look at the right velocities there and say that these one are the equilibrium velocities, also the right ones. So here. Now we have the equilibrium discrete velocities and can then go on into our first major step of every lattice-boltzmann method, which will be the collision step. So we do collide according to BGK. So we say discrete velocities post collision. So let's look at the computation. Here we say they are this one. So the updated discrete velocities are the discrete velocities minus the relaxation. And then here we have the difference between the discrete velocities and the discrete velocities in equilibrium state. So we do discrete velocities previous minus relaxation omega multiplied with discrete velocity previous iteration minus equilibrium discrete velocities. Then step number 6, we can do the bounce back boundary conditions. So bounce back boundary conditions to enforce the no slip, which is on the cylinder. And here I want to do an iteration over all the discrete velocities because this is hard to vectorize. So we say for I in range of n discrete velocities and say that the discrete velocities post collision are the discrete velocities post-collision at the obstacle mask, and then the lattice indices I. It's kind of optional because in the lattice indices, if you remember, these are also just values 0, 1, 2, 3, 4, and so on. But this one will then be set to the discrete velocities previous at the obstacle mask and the opposite lattice indices index I. Okay, let me decipher what is happening here. So the discrete velocities after the collision are augmented here if they belong to the obstacle mask and are set to the opposite values. And that makes sense because later on we will stream alongside our velocities, and if we now strategically inverse them, they cannot flow into our obstacle. So in other words, we have enforced the no-slip. And in essence, we are doing this for all the lattice indices such that we set them always to the opposite direction. Okay, then the last step, number 7. So we have 7, which will be stream alongside lattice velocities. And here I will also use a looping again. So for I in range of n discrete velocities. And for this, I will first create a new field. Let me call this discrete velocities streamed. And these are just the discrete velocities post-collision. And then we will augment them by saying discrete velocities streamed are the discrete velocities streamed at all points. So all points in x, all points in y, and then the I indicating the discrete velocity we're at. And this one will be set. And now we have to move our velocities according to the direction. So this works as following, that the value that is, for instance, associated with discrete velocity number 5 will move to the vertex on the top right of the domain. So imagine, for instance, we would have 9 neighbor vertices here. Then the 5 would move there, the 1 velocity would move there, and so on and so forth. And this one would also move over the domain boundaries. So for instance, if we have an velocity that is here pointing upwards, this would re-enter at the bottom. And by this, we automatically prescribe the periodic boundary conditions in that one. And by our preparations that we did, the velocities are not flowing from the right to the left, which is ensured by the Suhe scheme and by the outflow boundary condition that we already prescribed. Long story short, how are we doing that? There is a command in NumPy and therefore also in JAX NumPy, which is called jnp.roll. And we have to roll over all the x components as well as the y components. So I will do a nested roll over the discrete velocities post-collision, all points in x, all points in y, and then I for the index of the discrete velocity we're at. And then jnp.roll, if you look at the documentation, it takes an array as well as shift and an axis. So we want to shift in the first roll that we do in the direction of the velocities, or here I will do 0 because we are in the x direction, and then we also stream over the x batching. And then for the second roll, we stream in the direction of y. So lattice velocities 1i and axis is 1, which is the y batching. And with this very last step, we have our update routine finished, so we can return the discrete velocities streamed. And with this, we have finished one temporal iteration. We now have to wrap this update routine in our time loop. First, we have to create the initial velocity profile, and we are just super simple there. We take the velocity profile that we actually only want to have at the left boundary and say it's everywhere over the domain for simplicity. And this one will then define the discrete velocities previous. And now we need something to map from macroscopic to our mesoscopic discrete velocities. And we will just use the equilibrium function. So let's say get equilibrium discrete velocities. And this one takes our velocity profile as mentioned. And we also need a density. And just for simplicity, we assume a 1 density all around the domain. So I will just do jnp.ones of the shape endpoints x and endpoints y. And this should give us our initial velocity profile in the mesoscopic velocities. And then we can start with our time iteration by saying for iteration index in TQDM range n iterations. And we first call our function to update the discrete velocities. And then we can say discrete velocities next are update on the discrete velocities previous. And then we could just advance them, and by saying discrete velocities previous are discrete velocities next. And this should actually already compute. I will not let this run for now because we also want to implement the visualization. So let's do that. So let's implement the corresponding switch by saying if the iteration index modulo the plot every n steps is 0, so that we only plot every 100 iterations that we wanted, and the visualize flag is set to true, and the iteration index is greater than the skip iteration index, which we set to 0 for the start. And if this all is the case, then I want to visualize. For this, we have to transfer our mesoscopic velocities back into macroscopic velocities, and we have a function for that. Let's use this. First, of course, we have to define a density by saying get density on the discrete velocities next. And then we can define our macroscopic velocities according to get macroscopic velocities and plug in the discrete velocities next and the density. And if you looked closely at the plot from the intro, I want to have 2 subplots. In the top subplot, I want to visualize the velocity magnitude, and in the bottom subplot, I want to visualize the vorticity magnitude. That means how swirly the velocity field is at each point in the domain. So for this, we have to compute velocity magnitude and curl. So I will start off with velocity magnitude, and that's fairly simple by using jnp linalg.norm on our macroscopic velocities over the very last axis. And I want to use order 2, which is the Euclidean norm, so the length of the vector. For the curl, we need derivatives. So we need the derivative of the u velocity with respect to x and the u velocity with respect to y. And this can be obtained by calling jnp.gradient, which is finite differencing on the arrays on our macroscopic velocities. And I will use these ellipsis syntax. So I'm selecting all the x components of the velocity over our entire mesh. And let's do the same for the y component of the velocity. So dv dx and dv dy is jnp.gradient macroscopic velocities. And then we have a y1 here. And then the curl is defined as du by dy minus dv by dx. And then we can visualize all of this. So first we have an velocity magnitude contour plot in the top. For this I will say plt.subplot 2, 1, 1, which means we have 2 plots in the rows and 1 plot in the column, and we are at plot index 1. And then we do plt.contourf on grid x, grid y, and velocity magnitude. And I want to have 50 levels, so 50 contour lines. That just gives a smooth picture. And here I want to use the following color map. So CMAC map is cmr.amber. That looks really beautiful. Then let's say plt.colorbar to activate the color bar. And I will also set the label of the color bar to velocity magnitude. And I want to add a patch where the cylinder is, such that we know where the cylinder was when it was simulated by saying plt.gca, get current axis, and then say add patch, and I will add a circle here, and the circle is defined by x and y center, so cylinder center index x and cylinder center index y, and a radius, which is cylinder radius indices, and the color, I want to make it dark green, which is probably visually not the best choice, but feel free to adapt that. And the second plot is our vorticity magnitude. So vorticity magnitude contour plot in the bottom, or in other words, the curl. So we say plt.subplot 212. So we again have two plots in the rows, one plot in the columns, and we are now at plot index number 2. So we do plt.contourf here and say x, y, curl, and do the levels to 50 again. The CMap shall be cmr.redshift. That looks really nice. So redshift, not redshift. Then Vmin is minus 0.02 and Vmax shall be 0.02. These are values for which we want to cut off the coloring. I figured them out. They look quite nice. So we have on average, or like in peaks, vorticities between minus 0.02 and 0.02, such that we don't see some glitches that could happen there. But feel free to adapt that also if you change the Reynolds number. Then finally, let's also activate the color bar here and set its label to vorticity magnitude. And then let's grab the current axis again and also add the patch here, or maybe simplest would be just to copy that. And then we have to update that live by saying plt.draw and then plt.pause a little small time in order to swap the buffers. And then lastly, plt.clf in order to clear the figure. And then in the end, I just want to say if visualize plt.show such that when our simulation finishes, it will still keep the plot running. Okay, now is the moment of truth. In case we made any bugs, we will now see them, but let's just figure that out. Python lattice-boltzmann method. And here we see that I probably made a mistake. Exactly, so here I need to use the add in order to mutate the array or pseudo-mutate the array. So then let's run this and we see, okay, it works, but it doesn't plot. That's because we set the plot every number so high. So let's maybe put that to 5 and see if that works. So let's start visualizing it. And here we go. That should be our plot. And we see, okay, that's not going into the right direction. So I took some look around and I actually found that we made a mistake here in the lattice weights. So this one should be 36. Probably you spotted that mistake then. So let's set this one to 36. And of course that would explain why there was this unstable behavior. We had some diverging instability. Yes, that looks way better. So now we see some wave fronts also creating here. Because the problem was that if that is not 1 over 36, these lattice weights would not add up to 1, which is a crucial condition for the scheme to be stable. And here we see, okay, well, that's going rather slow. And imagine we wanted to do 15,000 iterations. That probably takes forever. And the big key now is, because right now our code with JAX is only merely faster than NumPy, but the big advantage of JAX is that we can just in time compile our update routine. And it's super simple. We just add the jax.jit. And if we now look at this, it runs extremely fast. So let's just start it. And now it compiles and it runs. And it's so fast now that our plotting is a little slowing it down. So let's go back to the 100 for the plot every, where is it? Here. So let's say 100, and you will see it's blazing fast. So let's hit it, and it's compiled, and there it runs. That's amazing. And here we see that the flow is flowing over the obstacle, and then there we see the flow pattern creating, and the vortex shedding isn't happening. It starts at roughly 5,000 iterations, but I think you see where it is heading. Let me close that down for a second, and let me change that to 5,000, such that we don't have to wait for so long the next time. And I also want to add some styling options, some last ones, which I think look beautiful, by saying here just right before the time iteration, plt.style.use dark background. And let me say we create a figure that has a figure size of 15 by 6 and a DPI of 100. Maybe you have to adjust that on your machine. And then let's run it. And now you see it should be the same as it was in the intro. And you see how fast it runs. That's just incredible. 500 iterations a second. You couldn't achieve that with pure NumPy. JAX is just amazing. And if you run it on a GPU, it's even faster. It's just mind-blowing. Okay, but now back to where we are. So here we see that the vertex shedding is starting. So we also see this in the velocity magnitude, that we have these kind of oscillating patterns. And in the beginning, the vortices are moving a little more towards the edges of our domain. And due to the periodicity, you will also see them re-entering. So maybe like follow the blue and you see it's re-entering there, and so on and so forth. But when it reaches some sort of like a steady state, it's producing vortices at a certain frequencies, and they are somewhat consistent. And it's just really beautiful to look at, especially also with the velocity magnitude. And I would encourage you to play around with it. So maybe you can discover something that can be done with a change in the parameters, or maybe take a deeper look. Or also you have a great GPU and can run it at even higher resolutions in real time. Just mind-blowing. Okay, that's the end of this super long video. Thanks for staying all the way to the end. It's also quite a difficult one, because we need some advanced NumPy or JAX NumPy tricks in order to make this run as fast as it runs. I would encourage you to download the file from the video description of the GitHub repo of the channel and just play around with parameters. And I think also if you look at the more difficult operations the implementation operations, then I think they might also come clear over time, and there's a lot to learn from that. Okay, if you enjoyed the video, then please consider liking and subscribing. I would extremely appreciate this. Other videos of the channel are quite similar to this, so also take a look around there. And if you enjoyed it, I would be happy to see you in the next video.